We can position our camera using many different functions. One very convenient function for positioning the camera is the LookAt function, which we'll study in this lecture. And we'll also look at the model view matrix for orthographic viewing. The LookAt function is provided in the glue library. It takes three parameters, which is the XYZ coordinates of the eye, followed by the XYZ coordinates of the center where the eye is looking at, and the XYZ coordinates, that is the up vector of the eye. And of course, by eye we mean the camera. So the camera position is given as three parameters which are of type GL double: X coordinate, Y coordinate, Z coordinates of the camera, X, Y, Z coordinate of the point to which the camera is looking. And of course, the camera could still be rotated to look at the same point, so we need to fix that rotation and define our up vector, the X, Y, Z coordinates of the up vector. Well, this function takes 9 input parameters. They are very simple and they are very convenient to define in terms of where we want to put our camera and where we want our camera to be looking at and how the camera should be oriented. So alternatively, we can use the LookAt function, which is provided in mat.h that comes with the book. The LookAt function will return to us a mat4 type matrix, which we can combine with other matrices to define our model view matrix. The input parameters of LookAt function are 3. It's just that it takes the coordinates in the form of vector 4, which is the homogeneous coordinate system, the XYZ coordinates followed by scaling. And the definition of these parameters is exactly the same: the eye position, the LookAt position, and the up vector of the camera. Here is an example where we'll use the LookAt function from mat.h, pass it on the eye, the add and up coordinates of the camera, and it returns to us a view matrix which is of type mat4. So hence we can now move our camera arbitrarily to any position and orient it in any way looking at any point. The default view of OpenGL is orthographic view. Orthographic projection will project a point P which is placed at X, Y, Z position to XP, YP, ZP, WP. Now XP is the same as X, YP is the same as Y. Because it is orthographic projection, there is no scaling of X, Y values performed here. However, ZP will be equal to 0 because everything is projected onto the camera plane or the image plane, which is placed at the Z is equal to 0. And the scaling factor is 1, hence there is no scaling performed. This can be represented by a 4x4 matrix where which is a diagonal matrix with 1 entries in the diagonal, except for when there is a Z coordinate entry in the diagonal, and of course this is the scaling factor. So we can start from an identity matrix and then set the Z parameter to 0 in the identity matrix like this and derive the orthographic projection matrix. And if you multiply this matrix with any point P in the XYZ coordinates, it will give us its orthographic projection on the Z is equal to 0 plane. So a very simple derivation of a model view matrix given here so that you can understand how projection is performed in its simplest form. So the OpenGL orthographic viewing function is called glortho. Right, so this will set up the orthographic view. Alternatively, if you want a little bit more control, you can use the simple ortho function from mat.h. Now notice that most functions in the core library that start with GL, ortho, and so on, or GL LookAt, the mat.h provides an alternative for that function which just skips the GL part. and more or less the parameters are similar. Sometimes they are given in a more convenient way, but here they are passed on exactly the same as they are passed on to GL ortho. The difference here is that this function will now return a mat4 matrix that you can combine with other matrices to get your final model view matrix. So let's look at what the parameters actually define. The left, right define the left and right planes where the view volume is cut. The bottom and up define, as the name suggests, the bottom and the top clipping planes, and the near and far then define where the planes are clipped at. So you can basically move your viewing volume to any position that starts from left, finishes at right, and then you can move it up and down to define your bottom and top position, and then you can move it forward or backwards and define your near and far positions for the view volume. This way you can set an orthographic view that is still orthographic, but the view volume is placed somewhere else.